Chapter 11, Section 4 begins with Hess's law. Hess's law tells us that the overall enthalpy change in a reaction is equal to the sum of the individual steps. So these ones will show you a balanced chemical equation, and this overall equation doesn't actually take place all at once. It actually happens in two steps. So first you have this methane gas combining with oxygen to make carbon dioxide and water vapor. Then the water vapor actually gets turned into liquid water. So those two steps combined make up this overall reaction. Now every reaction has its own change in enthalpy. So to find the overall enthalpy of this total reaction, we would have to add up the steps. So we would add the enthalpy of step 1 to step 2, and that will give us the total for this entire equation. And that's all Hess's law is. It's the sum of the steps. If the reaction occurs in 3 steps, 5 steps, doesn't matter. You still add up the enthalpies of each one of those individual steps, and that will give you your total enthalpy of your overall reaction. Heat of reaction refers to the energy absorbed or released during a chemical reaction, the standard heat of formation is symbolized by a delta H with a little F subscript and a degree symbol. That is the standard symbol, and we'll talk more about that here in a minute. So the standard heat of formation is the change in enthalpy when 1 mole of a compound is produced from free elements. So when you take individual elements and combine them to make a compound, that energy involved is the heat of formation. And these values are all listed in your book, Table A13, that begins on page 802. We'll be using these for some of our calculations, so you'll need to look them up, and you need to be careful that you check the state of matter when you're looking them up. So whenever you see that degree symbol, that means that standard conditions apply, and for thermodynamics, standard conditions are temperature equaling to 298 Kelvin or 25 degrees Celsius, and standard pressure is 1 atm, 1 atmosphere, or 760 millimeters of mercury. So anytime that degree symbol is present, these are the temperatures and pressures. The equations you'll be using look like this. You've got a delta H, and standard is equal to the sum of the delta H of formation for our products minus the sum of the delta H of formation for our reactants. So this equation can be used for enthalpy, it can be used for entropy, or it can be used for Gibbs free energy. So you'll take products minus reactants for each one of those, and all you need to do is look up the values from that table in the book, whether it's in the enthalpy column, the entropy column, or the Gibbs column, and that will allow you to calculate out these values. So here's a sample of an enthalpy problem. Now before, when we calculated enthalpy, we used Q over N or C delta T. This problem tells us calculate delta H for the following reaction. Is it exo or endothermic? And all it gives us is the balanced chemical equation. So we don't have joules, we don't have moles, we don't have molar heat capacity, and we don't have temperature change. So that leaves us this equation that we just wrote down. Delta H is equal to the sum of the delta H of the products minus delta H of the reactants. So I'm going to have to look up my products, add those values together, look up my reactants, add those values together, and then subtract the reactants from the products. Now what you'll see here, when I plugged in these values, I also multiplied them by how many moles were present. Now for this one, it doesn't necessarily matter because they're all 1-to-1 ratios. Okay, there's no coefficients in my balanced equation. If there were coefficients, you have to multiply the value that you look up by that value, by that coefficient. So if there were 2 water molecules here, then I would have to multiply this value by 2. So these numbers just came from table A13 in your book. Here were the products that I added together, here were the reactants, and I subtracted the products from reactants. That comes out to 41.2 kilojoules, and since it is a positive value, that means that this is an endothermic reaction. We do the same thing for entropy. So to calculate delta S for the reaction, does it proceed toward a more ordered or disordered state? It's the same equation, so I'm looking up the same types of substances in table A13, but I'm using the column that's for entropy as opposed to enthalpy. My equation is delta S is equal to the sum of the delta S of formation for products minus the formations of the reactants. And these are those values from table A13. This one is a positive value as well. And so that means that this is a more disordered state. So the products would be more disordered than our reactants. And the last one is Gibbs, and it's the same exact equation we've been using, only this time it asks us to find out if this reaction is spontaneous or not. So we need to calculate out Gibbs, and instead of using the enthalpy or entropy column in table A13, we'll be looking up these values in the Gibbs free energy column. This too comes out to be a positive value, which means that this reaction is non-spontaneous.